Okay, here we are. We are now in week 3, or near the end of week 3 for Bio 1140, our Biology for Health Sciences. So once again, if any of you have any questions that you'd like to ask me this week, feel free to shoot in the live chat. It should be up and going right now. So this week, what we're talking about is one of my favorite things. It's the ingredients, right? And one of the things that I always like to talk about in our biology class is how we are connected to the universe. I mean, it's pretty profound, isn't it? We have this really deep connection to the universe. And I'm about 2 minutes away from finishing the podcast. Sorry, yesterday I didn't get it up. I ended up having to go to town, and we had like we had two nails, one in each of our rear tires on the truck. So yeah, that was pretty crazy. That delayed us. You can imagine, we two nails in our rear tires and each one of them. So at any rate, but I'm about to get that podcast up on our connection to the universe. But to me, that is absolutely fascinating stuff. And one of the things that this for this chapter is to understand, like, we don't live in a vacuum here on the planet Earth. I mean, we are deeply, deeply connected to the universe through stellar processes. And it's kind of cliche, but you probably have heard your stardust. But it's true. I mean, we really are stardust. We're the remnants of stars that lived and died billions of years ago. Now, other things that this chapter is pretty good about. Other things in this chapter that are important that you will also need to know about is not just where the formation of the elements came from, but why elements are important and how they come together to form molecules. You'll need to make sure you understand why carbon is the element of life, why carbon is used to make organic molecules. That's incredibly important, and I talk about that. Also, you'll need to know about the bonding, especially covalent bonding. And I also talk about water and why water is vital for life to necessary requirements. And as we look for life elsewhere outside our own planet, one of the things we look for is liquid water. And the reason why is this series of chemical reactions, right? We rely on all these different chemical reactions, and water creates a medium for all these chemical reactions to take place. So that is why you are like 60 to 70% water, because you have all these chemical reactions of your metabolism taking place in it. And if it was an air, everything would be way too scattered. If it was a solid, the other problem with being on a solid is that the molecules would be locked in place and they couldn't move around. So life is dependent on liquid water, and you'll want to know why water is liquid at room temperature. So that's important. And of course, covalent hold hydrogen to oxygen to form a water molecule, but hydrogen bonds is what actually holds water molecules together to form liquid or even an ice. And you'll want to know about the importance of hydrogen bonds from creating liquid water. And it's also those hydrogen bonds that allow water to dissolve a great many things. So sugars dissolve in water. Why? They can form hydrogen bonds with it. Salts dissolve in water. Why? Because, well, hydrogen is a polar molecule. It's got a plus end and a minus end. And because of that, it can attract to the ions of sodium and chlorine and potassium and magnesium and calcium. So all of these ions can easily dissolve in water. So water is a good solvent. And water is also not a universal solvent. If it was a universal solvent, if you dropped water on your desk, it would just drill right through it. It just dissolve right through it. And of course, water is not a universal solvent. It's a good solvent. And then other properties of water that are important are the fact that, of course, it forms these hydrogen bonds, but also has a high heat capacity. What that basically means is it can absorb a lot of energy before it changes temperature, and it can give off a lot of energy before it changes temperature. And that's important as a like a thermal buffer. A thermal buffer, that sounds kind of complicated. Thermal just means heat. So if you walk outside at night and it's really cold, you don't immediately equilibrate with your environment. You don't immediately lose heat, and then because the water holds on to it. And then also when it's hot, it takes a lot of energy for that water to absorb heat before you overheat. So that's an important thing about this high heat capacity with water. And then the last thing I talk about with water are its pH. pH really matters, and you're probably doing some of that stuff in lab, where if you're taking the lab, if you're not, here's what pH is. pH measures the potential of hydrogen ions. You see, water, even though the individual water molecule is held together by covalent bonds, some of them come apart and it forms a hydrogen atom and a hydroxide atom. And actually, these are ions, so they're charged particles. And those are incredibly reactive. So because water, all the chemical processes of life take place in water, they depend on the pH. So if you become alkaline, where you have less and less hydrogen ions but more and more hydroxide ions, or you become more and more acidic, where you have more of these hydrogen ions, that changes the reactivity of the water, and it affects all the chemical reactions of life. So life is incredibly dependent on pH. And interestingly, there are organisms that can survive in pH so low, it's like battery acid. There are organisms that can survive on things that are incredibly alkaline, like oven cleaner. And then there's things like our blood. Our blood has a pH of around, oh gosh, I always forget, it's like 7.3 to 7.4. Any small change from that, and you can become too alkaline or too acid. You can go into acidosis, and like a change of like 2/10 in our pH can lead to death, right? Because our pH, our hemoglobin, which transports oxygen, is so finely tuned to its pH that any change, drastic change, can cause it to not be able to carry oxygen or carbon dioxide. Oxygen, of course, to our muscles and the rest of our body, and carbon dioxide back out. That a small change in the pH going to lead to death rather quickly. So that's not just to humans are we finely tuned to our pH, but the other thing I talk about too is acidic oceans. Well, actually, our oceans are not acidic; they're alkaline. They're about a pH of 8.1, with 7, of course, being neutral. And as we burn fossil fuels, we release carbon dioxide into the atmosphere, and that carbon dioxide absorbs in the water, and as it does so, it forms a carbonic acid, and that lowers the pH of the oceans. So the oceans are becoming more and more neutral rather than alkaline, and that's actually kind of bad for a lot of the organisms that live there, especially things like snails and corals. And of course, snails and corals, they build homes out of calcium carbonate, and calcium carbonate dissolves in water. And as the oceans become more and more acidic, that calcium carbonate becomes less available to life. Now, for the corals, this is a big deal. Coral reefs are amongst the most diverse areas on the planet, and they account for less than 1% of the Earth's surface area, of the ocean surface area, 1%, and yet they account for half of the ocean's diversity. And with the oceans becoming more and more alkaline, more and more toward neutral, the pH is going down, it's making it harder for these organisms to build their homes, which could have devastating effects on our diversity. And in fact, mass extinctions in the oceans have all been associated with ocean acidification. So pH matters, and what humans do is affecting that pH as well. Okay, so here I am. If anybody has any questions that about the material, like I said, go on live chat. You're free to ask me anything. I haven't gotten any questions yet, but I have had some from emails, and let me address these on email really quickly. First, science and digital literacy. Science and digital literacy assignments. To get full credit, you need to do some extra research. You need to research who those authors are. What are their credentials? And then you also need to research the subject matter itself. So if I'm talking about GMOs, what does the science say on GMOs? Or let's look at a past assignment on aspartame. I think that's one that's up now. What does the science actually say? Not what everybody thinks if it's bad or good for you, but what does the science actually say? So you need to do some research on that. The Wikipedia is a great resource to look stuff up, and that will help you with your decisions, and you have to explain these things rather well. Okay, I got a question. Well, we have a test review for chapters 1, 2, and 3. Well, here I am. I'm doing it right now. This is your chance to ask questions about those tests. Now, I have changed it for next week that, and if it doesn't work out this way, you have to let me. But you should be able to open up your test. It'll be timed at like 2 hours, but you should be able to open it up, look at it. If you don't understand something, you should be able to close it. It stops the timer. Oh, a bird just landed on my feeder out there. It's called a Say's Phoebe. But let me get back to this. So with the test here, you should be able to look at it, go through it. If you have a question, you should be able to close your test and then email me any questions you have about it. In terms of test reviews, like I said, I'll go live again next week on YouTube around, I'll do it before Thursday. I'll do it on Tuesday and Wednesday so that we can, so if you have any questions about the material, we can go over it. Okay, Savannah Weber. So when combined with hydrogen, would oxygen 18 form a polar bond, a covalent bond, of polar covalent bond, or ionic bond? Okay, so what you're asking there is there's, when oxygen binds to hydrogen, does it form, what kind of bond does it form? First of all, it forms a covalent bond. Now, co means with. Valent has to do with valence electrons. So imagine I've got an oxygen atom, and in the center is my nucleus, protons and neutrons. And then outside that nucleus, I have an electron shell. And that's where my electrons are. The first shell is going to hold 2 electrons. The second shell can hold up to 8, but oxygen is element number 8. So if it's element number 8, it's got 2 electrons in the inner shell, 6 out here. So it needs 2 more electrons. So it forms, so it shares the electrons, in this case with hydrogen. Hydrogen has a single proton with a single electron in its shell. So hydrogen will form a covalent bond with the oxygen. And what that does is you're sharing the electrons, and that's form a covalent bond. Now, covalent bonds come in 2 varieties. It's a continuum, but for our purposes, 2 varieties. They can share the electrons completely equally, like between carbon and carbon, oxygen and oxygen, carbon and hydrogen. That would be a non-polar covalent bond. Now, as we go to oxygen, oxygen has 8 protons in its center, in its nucleus. Those protons are positively charged. Electrons are negatively charged. Opposite charges attract. So when we form water, oxygen is way more electronegative than hydrogen. Electronegative means it attracts hydrogen. Attracts electrons. So what happens is the oxygen attracts the electrons to it. So the oxygen has the electrons spending more time near it, so it becomes slightly negatively charged. And because it's sharing those electrons unequally, it's hogging them away from the hydrogen, it forms a polar covalent bond. And as a result of forming a polar covalent bond, water is a polar molecule, right? So it's got a negative end up there by the oxygen, and the protons have a positive end. And because they've got this polarity to them, a plus and a minus end, these are partial charges, not full charges, they're not ions, they can still attract each other. So water molecules are attracted to each other through hydrogen bonding. So that was a really good question. So if anybody else has any other questions, let me know. I can tell you that historically on these tests, the questions that have given students the most problems are the questions on bonding, hydrogen bonds, covalent bonds, and ionic bonds. So you want to make sure you cover that. Even though the test is open book, open note, open web, I don't care what resources you use. Whenever I've given this test in class versus online, historically, the in-class group scores almost 10% higher. 10%, that's a full letter grade higher. And a lot of that has to do with people taking a test online. They do more poorly. Now, like I said, now this semester, I'm changing it up a little bit. So it's not like start to finish 2 hours. Once you open it, you must complete it within 2 hours. You can close it down and come back to it. And if it doesn't do that, you have to let me know so that we can work on that. And that way I can make myself available to answer any of your questions. Uh-oh, live chat's cutting out. I'm sorry. I'm on a slow internet connection. I'm at home, so yeah. Okay, I got another one. Does lemon juice preserve avocado? I don't know. Man, avocado, you cut it within hours, it starts turning brown, right? Because it's oxidizing with the air around it. Lemon juice will probably kill some of the bacteria on it, but it definitely tastes good with avocado, especially if you grind it up, add some seasoning salt. You can make some awesome guacamole. Man, I haven't had lunch yet. Okay, any other questions? Oh, one more thing about lemon juice. If you've ever marinated fish with lemon juice, it'll make the fish look cooked because the lemon juice is acidic and will denature the proteins, like heating your fish up. Although cooking your fish, so you make sure you get rid of all the parasites that could be in there. Okay, does anybody have any other questions here for this material? All right. Well, I'll keep in touch. Thank you for some of the responses from you guys out there. I've noticed that yeah, that some of you said the class is going smoothly. If there's anything I can do, always let me know. I got a couple more questions coming in. Okay, the difference between electron shell and electron orbital. I need a paper for this. Okay, I don't have my chalkboard here. I'm at home, but let me explain to you the difference. And you will not need to know this for this class, okay? And that's important. So if you accidentally come across a question about electron shells and orbitals, let me know, because I've removed the stuff about orbitals in terms of what you have to know. But if I were to draw an atom, this would represent shells. That would be the first shell. Oh, you can hardly see that. It's too bright in my office. Let's see if I can change this around. Yes, you can see I've drawn those circles. Those would represent electron shells. An electron shell is basically an area where you expect electrons to be based on energy level. Now, within a shell, electrons are specifically found in orbitals. And if we were to draw an orbital, it would look something like this. Okay, let me move my camera here so I don't have too much light on it. Okay, this would be our electron shells, and in this shell would be the sense we would have these orbitals. And basically these orbitals, these are where you're going to find the electrons most of the time, okay? And these orbitals, they hold up to 2 electrons. That's why whenever you see electrons, they're often done in pairs like this to represent the orbitals. And if you have something like hydrogen, they only have 1 shell here, and then carbon would have 1, 2, 3, 4, and that would represent 1 electron here, here, and here. So the orbitals only have 1, and then they would share an electron to fill that orbital. So you would share an electron to fill that orbital. I talk about that more in cell and molecular biology, the 2110. I used to talk about it in this class, but I've kind of dropped knowing the difference between shells and orbitals. But just know that an orbital is located within the shell. So I've tried to make it a little bit simpler here. Okay, so what are blogs? Oh gosh. Okay, so I copied this class from last semester when I had them do blogs. There are no blogs for this class. Anytime you see blog, forget it. Ignore it. Don't worry about it. It's not part of this class. It was an assignment from last semester. I keep trying to remove them all. Yeah, but I didn't want to rebuild my class from scratch, because to build this online class is really, it takes an intense amount of effort. I've been working on it for like 4 years. So sometimes things get copied from a previous semester that I haven't quite changed out yet. But yeah, no blogs, none for this semester. Just science and digital literacy. Okay, cool. Another question coming in. The elements in your body are made of subatomic particles that are what? Okay, so elements like carbon, nitrogen, oxygen, hydrogen. I mention this all the time because that's basically 96% of you are made up of tiny subatomic particles, and those are called protons. Protons equals your atomic mass, okay? And like I said, if you have an element, it's not exactly like 12 or so. It could be more. All right. Anybody else have any other questions here? I know you guys are starting to drop off a little bit. Oh, the video cut out as soon as I answered the question. Oh, no. Particles, protons, neutrons, and electrons. Protons are in the nucleus. Neutrons are in the nucleus. Neutrons are neutrally charged. Protons are positively charged. And electrons are negatively charged. And those are found, of course, in the electron shells. Okay. It looks like in the future I'm going to have to go to campus to do this. My connection looks like it's good. I don't know what's going on here. Everybody got that? Okay, any more questions? All right. Well, have a great weekend. Don't forget to turn in the quiz for quiz 3 on Sunday, and then you'll have all next week to take the test, and that will be the only assignment that you will have to do is the test next week. Okay, until next time.